In this lesson, we're going to be looking at Unit 6, Chapter 6, Trigonometric Identities. We're going to be again looking at reciprocal, quotient, and Pythagorean identities, but we're looking at Part 2, specifically non-permissible values. As we said, this is from Section 6.1. The focus is on determining non-permissible values of trigonometric identities. Let's start by first of all looking at the graphs of y equals sine x, which you see here, and the graph of y equals cosine x times tan x, which you see here. If you compare the two graphs, they certainly look to be identical. All the points on this graph certainly correspond with all the points on this graph. However, when we consider the table of values for both graphs, there is a slight difference. You will notice that most of these values are the same, but if you look real close at pi over 2 and 1 is a point on the graph of y equals sine x. However, when x is equal to pi over 2, cosine x times tan x is actually undefined. If you look at the graph, you will see that I've placed a dot at pi over 2 on the graph of sine x, but there is no dot on the graph at pi over 2 for cosine x times tan x. And the reason being is because it's undefined. There's actually an open dot at that location. We don't see it, but it's actually there. So this graph is actually undefined for that value of x. If you look a little closer, it's also undefined at 3 pi over 2. Again, there's no dot located here, only an open dot, whereas on the graph of y equals sine x, there is a solid dot. So this is a major difference that's occurring between the two graphs. If you look at the question that I've asked over here on the right, what are the non-permissible values of x in this equation? We can see that there are values of x where this graph is undefined. It's undefined at pi over 2. It's undefined at 3 pi over 2. Again, we end up with an open dot at these locations. So there are values of x where this graph is undefined. What are the other values of x? How can we write this as one single equation? Well, we can write it as x is equal to pi over 2 plus pi n, where n is an element of the integers. We have an open dot at pi over 2. We have an open dot at 3 pi over 2. We'll have another open dot at 5 pi over 2, and at 7 pi over 2, and so on. So every time we add pi, we will continue to get a location on the graph of cosine x times tan x that's undefined. So there are non-permissible values. And the reason why these non-permissible values exist is because of the fact that tan x is equal to sine x over cosine x. And we know that cosine x is undefined here because we know division by 0 is undefined. So we know that cosine x here cannot equal 0. Wherever cosine x is equal to 0, tan x is undefined. Where is cosine x equal to 0? Cosine x is equal to 0 at exactly the locations that I've highlighted up here. At pi over 2, and at 3 pi over 2, and so on. If you think about the graph of cosine x, and you all should have a good visual of the graph of cosine x, the graph of cosine x looks something like this, doesn't it? I'll just do a quick sketch of it here for you. Give me a second. The graph of cosine x looks something like this. And again, the question is, where is the graph of cosine x equal to 0? Graph of cosine x is equal to 0 here and here, which is at pi over 2 and at 3 pi over 2. And that's the reason why tan x is undefined when cosine x equals 0, because division by 0 is undefined. Can't be done. So if tan x is undefined when cosine x equals 0, then the graph of cosine x times tan x is also undefined at those same values, as you can see here. So although the two graphs look to be identical, there are some slight differences. Now, is this an identity? The answer is yes. Sine x equals cosine x times tan x is still an identity because it is true for all permissible values of x. And that's the definition of an identity. As long as it's true for all permissible values of x, both sides of the equation are true, then yes, this is an identity. It's just that there are non-permissible values in the equation. Let's look at how do we determine the non-permissible values. Well, I just showed you a small example there using tan x. Let's have a look at another example. Determine the non-permissible values in this equation. Secant x equals tan x over sine x. Very important here. We must consider the restrictions on each trigonometric function in the equation, first of all, And we need to consider any expressions that may have non-permissible values as well. For example, the expression tan x over sine x is undefined for sine x or sine theta is equal to 0. So we must consider two parts here. We must consider the restriction on each trig function first, and we got to consider any restrictions that occur because of expressions that exist in the equation. So let's look at the trig functions themselves first. Secant theta. Secant theta is equal to 1 over cosine theta. Secant theta is equal to 1 over cosine theta. Are there any values of theta when this is undefined? Of course there are. This is undefined when cosine theta is equal to 0. Cosine theta cannot equal 0 here, because if cosine theta is equal to 0, secant theta is undefined. So we're looking at our first trigonometric function. Let's look at tan theta. Tan theta is equal to sine theta over cosine theta. Are there any values of theta when this function is undefined? And again, the answer is yes, because cosine theta cannot equal 0. So it's the exact same values of theta that we have for secant theta. And what about sine theta? Are there any values of theta when sine theta is undefined? And the answer is no. There are no values of theta when sine theta is undefined. So that takes care of number 1. Number 2 says we must also consider any expressions that may have non-permissible values. If you look at the equation, there is an expression that has non-permissible values. If we consider the expression tan theta over sine theta cannot equal 0. Now, that's completely different than up here. Up here, I was just looking at the trigonometric functions themselves. Are there any values of theta when sine theta is undefined? The answer is no. Are there any values of theta when tan theta over sine theta is undefined? Yes. This expression is undefined when sine theta is equal to 0. So we have two things to consider. We have to consider when cosine theta is equal to 0 and when sine theta is equal to 0. Because we know that for all of these values of theta, this expression is undefined. This entire equation is undefined. So let's look at where cosine theta is equal to 0, because that's the values of theta that we're not allowed to have. So cosine theta is equal to 0 at these locations. At pi over 2, and at 3 pi over 2, at negative pi over 2, and at negative 3 pi over 2. So we can write x is equal to pi over 2 plus pi n, where n is the number of I, because you can see that this is the graph of cosine x. Now I've also graphed y equals sine x for you. Where is sine x equal to 0? Sine x is equal to 0 at 0, and at pi, and at 2 pi, at negative pi, and negative 2 pi. So at 0 plus pi n, where n is the number of I. At 0 plus pi, we keep adding pi or subtracting pi from 0, we will get values of x where sine x is equal to 0. So we have two sets of values that we need to consider. If we were to plot both sets of values on the same grid, or on the same graph, you should see that I would have 0. Just take these points and place them over here. I'd have 0, and pi, and 2 pi. I'd have pi over 2 and 3 pi over 2. You should see that the solution with both sets of points graphed on the same grid would represent these dots that I'm highlighting here. So how can I represent those yellow dots? Because that's both sets plotted together. The yellow dots would be represented simply as x equals 0, we don't need to say 0, plus pi over 2n, where n is the number of I. Here is the solution with both sets of solutions. This set and this set will combine into a single set, x equals pi over 2n, where n is the number of I. So there's the solution we're looking for. These are non-permissible values of x. Example 2. Again, this is a multiple choice. It might be a good idea for you to pause the recording and maybe try this one on your own first. It says on x being an element between 0 and pi, including 0 but not including pi, where's the graph of tan x times cosine x not equivalent to the graph of y equals sine x? Where is this graph not equivalent to this graph? Well, I think if you look at closely, this is the exact same graph that I did earlier. We looked at the graph of sine x, we looked at the graph of tan x times cosine x. Let's go back and look at them again. Sine x and tan x times cosine x. Right here. Here's the graph of sine x. Here's the graph of cosine x times tan x. It's undefined between 0 and pi. It just asks for between 0 and pi. Where is it undefined? It's undefined. The only value of theta, or x, where the two equations are not equal, is at pi over 2. So the correct answer to this question is at pi over 2. And again, if you want to, you can take out your graphing calculator, graph them, or we really need to be looking for a non-permissible value here, right? And the other way to do it other than graphing it is to think about this again. You know, tan x is equal to sine x over cosine x. And again, cosine x cannot equal to 0. Where is cosine x equal to 0? Between 0 and pi. That's what we're looking at. Where is cosine x equal to 0? Between 0 and pi. Here's pi. Cosine x is equal to 0 at pi over 2. Cosine x cannot equal 0 because this function is undefined when cosine x equals 0. So the correct answer again is pi over 2. A couple of ways you could have done that. Example 3. Which are the non-permissible values for x in the equation cosecant x over cotan x? Again, it might be a good idea for to pause the recording and try this one, but I've given you a hint here. You must consider the restrictions again on each trig function first, and then on any expression that may have non-permissible values as well. I'm going to do this. Cosecant x. Let's consider, first of all, the restrictions on each trig function. Cosecant x. So I'll call this number 1, number 1. Cosecant is equal to 1 over sine. So again, sine x cannot equal 0. Where is sine x equal to 0? That's the question, because wherever sine x is equal to 0, cosecant x is undefined. Again, you may want to just do a sketch of the graph of sine x to help you determine this. So I'll do that for you. The graph of sine x, you should have this memorized. It looks like this. Well, something like this. But the graph of sine x is equal to 0 at 0, and at pi, and at 2 pi. So I would write simply the answer pi n, where n is an element, oops, sorry, I left out the n, where n is an element of I. So again, these are the values of x where it's undefined. X cannot equal pi n where n is an element of I, because again, sine x is undefined for these values of x. Let's consider cotan x. Cotan x is equal to cosine x over sine x. The exact same thing occurs again. Sine x cannot equal 0 because division by 0 is undefined. So where is sine x equal to 0? Sine x is equal to 0 at the exact same places that I found above. So x cannot equal again pi n where n is the number of I. Now we must consider any expressions that may have non-permissible values. If we look at the expression, the entire thing, we can see now that cotan x cannot equal 0. So cotan x cannot equal 0. Cotan x cannot equal 0. Where is cotan x equal to 0? Now you're going to think about that one for a little while. Cotan is equal to cosine x over sine x. Where is cotan x equal to 0? Cotan x will be equal to 0 when cosine x equals 0. Because your numerator here of 0 will give cotan x equal to 0. And cotan x can't be 0. Cotan x will be 0 when cosine x equals 0. So now we need to consider the graph of cosine x. Cosine x looks like this. A second here, I change the color. Takes a while sometimes. Here we go. So where's cosine x equal to 0? Cosine x is equal to 0 at this location, and at this location, and this location, which is at pi over 2, and at 3 pi over 2 again. So cosine x equals 0. We know that cosine x cannot equal 0, so x cannot equal pi over 2 plus pi n, where n is the limit of I. So again, we need to combine these solutions if we can. Let's combine the solution x equals pi n and x equals pi over 2 plus pi n. If you combine those two solutions, you will get one solution, exactly like the one I did before. It's simply pi over 2 plus, 0 plus pi over 2n. 0 plus pi over 2n. That's all we need. Because 0 is an answer, pi over 2 is an answer, pi is an answer, 3 pi over 2 is an answer, 2 pi is an answer. All of these are inadmissible values. So to combine these two sets of solutions again, I will combine them into one solution to be x cannot equal pi over 2 n, where n is the limit of I. These are the exact same two solutions that I did earlier in this one right here. Right? I combined pi over 2 plus pi n and pi n into one single solution, and you saw where I plotted them here as pi over 2n, where n is the limit of I. The exact same thing occurred here. The exact same set of solutions were combined to get an answer of A. Again, if you want, you can actually plot the points on a grid to show that these points, when plotted, will form this solution that I've indicated here. There's one set of points. If I took the points that I had for cosine now and plotted on this grid with the others, I would get this set of points here. Plot it with it, you see, which would be pi over 2 and 3 pi over 2. And you should see that all those points now together can be represented simply like this. All of them together can be represented as pi over 2 n. Because we're increasing the multiples of pi over 2. Example 4. What are the non-permissible values of x for this expression? Again, let's consider both scenarios here. Again, we need to consider restrictions on each trig function. If we look at tan x first, tan x equals sine x over cosine x. So again, cosine x cannot equal 0 because division by 0 is undefined. So where is cosine x equal to 0? I've got the graph of cosine here for you again. It's at pi over 2 plus pi n. Pi over 2 plus pi n, where n is the number of I. Because again, you keep adding pi, you'll get the next answer. Okay, we need to consider cosine x. That's a trig identity, or a trig function. Are there any values of x where cosine x is not equal to, can't be equal to 0? No. No problems here. No problem with this one. However, when we now consider the expressions, is there any non-permissible values that occur as a result of the expression itself? And the answer is yes. Now when we look at the entire expression, I'm sure you'll agree that my denominator cannot equal 0. So cosine x plus 1 cannot equal 0. So if cosine x plus 1 cannot equal 0, then cosine x cannot equal negative 1. Where is cosine x equal to negative 1? Cosine x is equal to negative 1 here and here. So cosine x can equal negative pi or pi, and so on. Now, if we want to write this as a general solution, you see 2 pi is not an answer, 0 is not an answer. So I can write x cannot equal pi plus 2 pi n, where n is the number of I. So this is a set of non-permissible values, and this is a set of non-permissible values. Now, can I combine those two into a single solution? And the answer is no. I cannot. My solution for this equation here consists of both this set and this set. If you look at them, I can't combine these into a single set because there are values that are missing. Like you might think maybe pi over 2 plus pi n, but that will not do it. If you look at your red dots and your green dots, which I've plotted now on the same grid, there's no way of representing these red dots and green dots as a single solution because there are other green dots here. Maybe I should plot them. There's an answer there. There's an answer there corresponding with these answers here. But again, if you look at them, there are other values. We just can't say pi over 2 plus pi over 2n because 0 is not a solution. 2 pi is not a solution. So because of that, we can't do that. We just need to leave them as two separate sets of non-permissible values. So the answer this time is actually x equals, and I would write it like this, pi plus 2 pi n, where n is the number of I, and pi over 2 plus pi n, where n is the number of I. That's my solution. Okay, key ideas. To find non-permissible values, we must consider the restrictions on each trig function in the equation and any expressions that may have non-permissible values. You've got to consider both. That ends this lesson.